Data. It's everywhere. From the number of steps you take to the price of bread. This data, like people, has different personalities. We call these personalities data distributions. Imagine data as a school of fish. Sometimes the fish swim uniformly, spread evenly across the ocean. That's uniform distribution. Other times they cluster together, forming a familiar bell shape. This is normal distribution, very common in nature. But fish, like data, can be unpredictable. Sometimes they group near the surface or dive deep down. This is skewed distribution. Understanding these fish formations helps us make sense of the vast ocean of data. Let's dive deeper, shall we? Imagine rolling a fair die. Each face, from 1 to 6, has an equal chance of landing face up. This is uniform distribution in action. Each outcome is equally likely. Think of a lottery draw where every number has an equal chance of being picked. This fairness, this equal probability, is the hallmark of uniform distribution. In real life, pure uniform distribution is rare, but it serves as a fundamental concept, a baseline for understanding other distributions. To create a uniformly distributed data in Python, we use random.uniform function from NumPy library. The first two values gives the range and the last value is the size. In the example, the data generated ranges from a low value of 0 to a high value of 10 and 1000 data points are created. Then we use hist function from the Matplotlib library to create a histogram of those data values. We can add title, xlabel and ilabel as shown. Next, we'll explore the most famous distribution of them all, the normal distribution. The normal distribution, often depicted as a bell curve, is everywhere. Human height, shoe sizes, even exam scores often follow this pattern. Imagine measuring the height of all adult women in a city. Most heights will cluster around the average, with fewer people at the extremes, very tall or very short. This creates the bell shape. The normal distribution is crucial in statistics. It helps us predict probabilities and understand the characteristics of many data sets. The example Python code shows how to use random.normal function from NumPy library to create a dataset. The first number in the function is the mean, the second number is the standard deviation, and the third number is the total number of data points. So it creates a normal distribution around a mean value of 50 with deviation of 10 and 1000 data points. Play with these values to observe the changes in the graph. But not all data follows this neat bell curve. Let's explore why. Life is full of surprises, and so is data. Sometimes data leans to one side, like a leaning tower. This is skewed distribution. Imagine the income distribution in a country. Most people might earn within a certain range, but a few very high earners skew the distribution to the right. Skewness can be positive, with the tail on the right, or negative, with the tail on the left. It tells us about outliers and unusual data points. Understanding skewness helps us interpret data accurately and avoid misleading conclusions. A skewed distribution is a probability distribution where the data is not symmetrical around the mean. In Python, we use skewNorm from scipy.stats to create a skewed distribution. The value of A determines the skewness. For positive A, the curve will be right skewed. For negative A, the curve will be left skewed, and when it is 0, it will be symmetric normal distribution. The Matplotlib plot functions plots the right and left skewed distribution with blue and orange colors respectively. Section 5. Measuring the spread variance and standard deviation. We've seen how data can be distributed, but how do we measure its spread or variability? Enter variance and standard deviation. Imagine two groups of students taking a test. Both groups have an average score of 70%. However, the scores in one group are tightly clustered around 70%, while the other group has scores spread out from 50% to 90%. Variance quantifies this spread. A high variance means data points are far from the average, while a low variance indicates clustering. Standard deviation is simply the square root of variance. It gives us a more interpretable measure of spread in the same units as the original data. These concepts are crucial for understanding the variability within a dataset. The std function from NumPy is used to calculate the standard deviation. In the example, we have used green-colored dashed line to represent +1 standard deviation, and green-colored dashed line to represent -1 standard deviation. The function legend from Matplotlib is used to show the legend. As before, you can play with different parameters in the random.normal function to change the shape of the plot. Section 6. Navigating percentiles. Understanding data position. Percentiles tell us the relative standing of a data point within a dataset. They divide data into 100 equal parts. Imagine you scored in the 80th percentile on an exam. This means you scored better than 80% of the test takers. Percentiles are widely used to understand data distribution and make comparisons. For example, growth charts for children use percentiles to track their development relative to other children. Understanding percentiles helps us interpret individual data points in the context of the entire dataset. We use percentile function from NumPy library to calculate the given percentile value. In the example, 25th and 75th percentiles are plotted. If the distribution is the salary of 100,000 people with 50 mean and standard deviation of 10, it tells us that 25% of the people's income is below 43.26. Section 7. Data visualization with Seaborn. Painting a clearer picture. While Matplotlib is powerful, Seaborn takes data visualization to the next level. Built on top of Matplotlib, Seaborn provides a higher-level interface and aesthetically pleasing visuals. Imagine creating a heat map to show the correlation between different variables in a dataset. Seaborn makes this task effortless, generating visually appealing and informative heat maps with just a few lines of code. Seaborn excels at creating statistically insightful plots, such as violin plots, box plots, and pair plots, which are particularly useful for exploring distributions and relationships within data. By combining powerful visualization techniques with an intuitive interface, Seaborn empowers us to uncover hidden patterns and communicate complex data stories effectively. In the example, we have used Seaborn to visualize data more beautifully. You can see how boxplot, scatterplot, and heatmap are created. Section 9. The power of data understanding our world. Data is everywhere, shaping our decisions and understanding of the world. From predicting the weather to tracking disease outbreaks, data analysis plays a crucial role in modern society. By understanding data distributions, we can make sense of patterns, identify trends, and draw meaningful conclusions. Visualization tools like Matplotlib and Seaborn empower us to communicate these insights effectively. As we navigate an increasingly data-driven world, mastering data distribution and visualization will be essential for informed decision-making and a deeper understanding of the world around us. In the next lecture, we are going to learn about predictive models such as linear regression and polynomial regression and using these models for data prediction. So, stay tuned and please subscribe.